So in this week's lab, we're going to be talking about interfacing the microcontroller, the Arduino, to a microphone. We're going to be able to see a lot of things about interfacing to a microphone, and you're going to have, I think, a pretty interesting experience with doing so. The first thing to know is that we are using actually a device that is a combination of a microphone and an amplifier. So whereas in the amplifiers lab, we had, I think it was 5 operational amplifiers, and then we had to interface that to a microphone. That's all built onto a device that's, less than a square inch, probably a half a square inch. So this is going to be a very nice compact device. You can see on the back here all of the resistors and the integrated circuits that are necessary for doing the amplification. So when we're working with these microphones, one thing that we want to be careful about is we want to try to minimize the noise. Now, noise means two things in electrical systems. It means both audible noise and electronic noise. Now, unfortunately, we're not going to be able to minimize the audible noise because you're going to be doing this in a room with 9 other groups, and they're all going to be clapping and talking and making noises, and that's just something that we have to accept because of the environment that we have. There's also going to be the hum of the HVAC vents. There's nothing that we can do to eliminate that either. Ideally, you'd be doing this just one team, maybe even just one person in a very soundproof room, but we don't have control over that. But what we can control is the electrical noise, the electronic noise. And I've got an 8-step process here for minimizing the electrical noise in the system. And please take this seriously, because all the stuff toward the second half of the lab will not work correctly unless you make these connections exactly as they're laid out here. I don't emphasize things very often, but I'm really trying to emphasize this because honestly it took me about a week and a half to write this lab, and at least a week of that was wasted because I just had too much noise in the system. So please, 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 seriously, make the connections very carefully that are outlined here in these 8 steps. So once you've done that, then you can go ahead and construct or edit the first program. What we're doing here is we're simply going to be reading in a signal, and we're going to display it out to the serial monitor. You'll see here that I'm using, for example, this analog reference external. Well, that's actually up here. If you look in this step, it says connect the AREF pin from the Arduino to the 3.3 volt power supply that's going to the microphone module. This AREF is the analog reference signal, and to be able to consider that as the maximum voltage that the analog signal could expect to see, we need to issue this command. If we don't do this, then it actually uses the power supply that's being used to power the 5 volt bus of the microcontroller, and as we're going to see pretty soon, that's not a very good signal. It's got a lot of noise in it. You can see here that in loop, really all that it does is collects a sample and then it prints it out to the screen. Now this collect sample function has some meat on the bone, so we need to understand what that's doing. Let's look here at collect sample. So first of all, I'm going to start a timer. So this millis is how many milliseconds has it been since the program began running, and that can go for like 50 days before it's going to wrap around. So as long as we haven't run the program for more than 50 days, it should be just fine. We're going to have an amplitude, we're going to have a sample, we're going to keep track of the minimum and the maximum. And what we're doing is we're setting the max to 0 and the min to 1024, so that essentially any other signal will quickly become the min or the max. We're saying here that as long as the current milliseconds minus the start milliseconds is less than the sample size, where the sample in this case is 50 milliseconds, then go ahead and take another sample. So I'm going to sample, which is just doing an analog read, just like in the analog lab. And then I'm going to say, okay, if it's larger than the current max, then it is the new max. And if it's smaller than the current min, then it is the new min. So what I'm doing is for 50 milliseconds, I'm trying to find the very largest value that I read and the very smallest value that I read. We're going to calculate the amplitude as being the difference between those two. Then I'm going to remap this because I know that the A to D converter, the analog read command, can return a value that's as low as 0 or as high as 1023, but I don't want to output those. I want to put it on a percent scale. So I want to output a value between 0 and 1000. So this map command, by the way, would have come in really handy when we were doing that thing with the temperature where you had to squeeze the thermistor to be able to adjust the temperature, but I wanted you to do that manually at the time. Now you know enough that I don't need you to do this manually anymore. So we're going to adjust the range from 0 to 1023 up to 0 up to 100. And then we just return the amplitude. So this is the process we're going to do to collect samples in both of the first 2 labs. So that's pretty much what goes on there. We're going to collect the sample, and then you're going to open the serial plotter to be able to see the signal. And so when you do that, you're going to get a good result, and you're going to be able to see on the screen. You'll be able to see the audio signal visually changing with time. So that's sort of our initial pass, and then I encourage you to try using the 5-volt power supply instead of the 3.3-volt power supply, and you'll see that it's a lot noisier. And there's and this, honestly, the signal would not get very good results if we use the 5-volt power supply. And then please be sure to move the wire back to the 3.3-volt pen, because if you leave it on the 5-volt pen, you're going to have noise for the rest of the lab. Now we're going to we're going to build a thing called a smart clapper. And smart clapper used to be a project that we would have juniors and seniors work on, but now it's a project that freshmen complete in one lab period, actually a fraction of a lab period. What I want you to do is connect pins 9, 10, 11, and 12 to the 4 LEDs that you'll find on your breadboard this week. And that's really the only additional hardware you need to connect here. What we're going to do is we're going to flash the first LED, it's the blue one. We'll flash that every time that a clap is detected. And then if one clap is detected, we'll toggle the second LED. 2 claps will toggle the third LED. 4 claps will toggle the fifth LED, or the fourth LED. So you can see here that I've introduced a couple of delays and a threshold. This threshold, by the way, I'm saying anything above 50 would be detected as a clap. Now you might want to raise that to 90 or 95 to make sure that it's really a nice loud clap, because even when I talk near the microphone, I'm actually exceeding a threshold of 50. So that's something for you to consider adjusting. And this shows which pins go to which of the LEDs. We set those LEDs up as being outputs. We take the analog reference to be external. Come down here, and in loop, all we're doing is we're sitting here waiting for the first threshold, or for the first time that the voltage exceeds the threshold. It would sit there forever if it never exceeded the threshold. But once it does, then we're gonna say, okay, we've already detected one quote clap. Now I'm going to start a 1-second timer, and if I detect a second clap during that 1 second, then I'm going to go ahead and increment the counter and restart the timer. So notice that clap time is initialized as whatever the current milliseconds is. But if I detect another clap, then I say, oh, there's been a second or a third or a fourth clap. Time to restart the counter, restart the timer. So I have another second to hit a second or a third or a fourth clap. But ultimately, I'm going to fall through this loop because a full second has elapsed without detecting a clap. And then I'm going to toggle. Notice here what I'm doing is I'm saying, okay, if counter is 1, so if 1 clap was detected, then I want to write onto green, not what I read from green. So if I read a 0, I want to write a 1. If I read a 1, I want to write a 0. This is a very clever way of toggling a current digital output. It's the same collect sample that we had last time. I don't believe anything changed except I added this display blue command. And so display blue is just going to say anytime that I exceed the threshold, I'm going to flash the blue, the first LED. And I'm going to introduce a 1/10 of a second delay, so I can't have clap, clap. I want to have at least a 1/10 of a second between the claps. And if I don't detect a clap, then I'm going to turn off the blue. Okay, so there's a lot of discussion of this and talking about them. Think about what would happen if you clapped 4 times, 5 times, or 6 times. What would happen? What would change in the 4 LEDs? And then I'd like you to make a change. It's actually just one character that you have to change in the whole program that would make it so that the red LED, the fourth LED, will toggle if 3 or more claps are detected. So that's not a very big change. Then we're gonna actually visualize the output or the audio signal. We're gonna visualize that on this matrix LED display. And so you can see the matrix LED on the front. If you flip it over on the back, you can see this device. This is actually an integrated circuit that receives the serial input, and then it's going to one by one, it'll light these LEDs corresponding to the device, or corresponding to the signal that it has received on the serial input. It requires only 4 connections, and the ground and the power have already been made for you. So you're going to need to have the clock, the SCL, and the data, the SDA, serial clock and serial data. Those are the only 2 connections you're going to need to make to be able to connect this device. And down here, it's going to describe how to do this. The C, the serial clock, is going to be connected to pin A5, and the D, the serial data, is going to be connected to pin A4. Pin A5 and A4 are usually used as analog inputs, but they can also be used to implement what's called an I2C interface. And so this I2C interface is going to allow us to have this serial port connection that's going to allow us to make the communication from our Arduino to this LED matrix. Now, in order to be able to make this connection, you're going to need to install a few libraries. You need to institute or activate the wire library, and it gives you very detailed instructions of how to do that. I would just encourage you to follow those instructions carefully. The wire library is shipped with the Arduino interface, but it's not activated. So there's lots of libraries that are shipped with it. You have to activate them if you want them. We also need to install 3 additional libraries that are not shipped with the Arduino interface. And so those are zip files. They're stored on Blackboard. Download the zip files, put them in a location where you can easily find them, and then follow this procedure to add those zip libraries to the system. So now it's time to test the LED matrix. There's a practice or sort of an example code that you can use to do that. And that will give you a nice demonstration of what the matrix LED can do. Once that displays, you've actually got the hardware set up correct for the rest of the lab. Now it's just a matter of using a combination of the microphone and the matrix LED. The first thing we're going to do is we're going to visualize some audio. And so I've got a program here that you can run. And essentially, it's going to display, and I don't want to go into the details of this. You can look over the code. The one thing that I'll say is that drawing this sample onto the screen, we're going to shift each of the columns one place to the left, and then we're going to construct the new column. We're going to either turn each pixel off, or we're going to light each pixel green, or we're going to light each pixel red. So each individual pixel will either be turned off, lit green, or lit red. And it's only the top 2 bars that would be possibly red. That's to indicate, oh, we got a pretty hot signal here. It may be that we need to decrease the amplification there. And once we've constructed all of that, we'll issue this command matrix.write display, and that will send the signal out to the display, and it'll update that signal. So here we're going to see that we can, this actually just talks a lot about that. So that's really all that I wanted to tell you about that. This will then display the voltage that's being measured as a function of time. So as you say a word or as you snap your fingers, it will be displayed immediately upon the LED matrix. As you progress, you might be able to see that there are other things that you could do. You know, you can clap, you can whistle, you can try doing things like that and see what it does to the display. But the most interesting thing we're going to do is the very last thing, and that's visualizing the frequency response. So that rather than having the display depend on time, now the display is going to depend on frequency. It's very much like a graphic equalizer where the lower frequencies are on the left and then they work up to higher frequencies toward the right. And so if you play the demonstration video, you'll be able to see the application of the frequency response. We're going to have a function here, an algorithm called the fast Fourier transform, or the FFT. And the FFT is another library. In fact, it was one of the 3 libraries that you installed in the previous section. So you can see here FFT.h. And a lot of this program, I'm going to be honest with you, is beyond the scope of this course entirely. Stuff like the FFT window, FFT reorder. These are things that I don't really think that it's necessary to explain them right now. Just understand that they need to be done so that we can get the correct FFT result. If you want to dig more deeply into that, I've, again, spent quite a bit of time preparing this lab, and I'd be happy to talk to you about it. But I think that for right now, what I want you to see is that this program can display the frequency response with lower frequencies toward the left and higher frequencies toward the right. This is something that will come up to be very important to you in your junior and senior year, and I wanted you to see this frequency response at least one time in your freshman year. So once you've completed that, then just demonstrate it to your professor or the lab assistant, and you'll be good to go for the week.